Hello everyone. I'm Pragati Pradhan, currently a postdoc at MIT Kavli, working majorly with David Hunemoder and Moritz Gunther. So today I'm going to be talking about the colliding in binary WR25 with Chandra HETG. Now this whole work has been a team effort, and especially David has been very involved with the whole analysis and the nitty-gritties revolving around high resolution spectrum. And I have also had a lot of fun working with the other co-Is. So I'll start with what are colliding wind binaries. Basically, when we have two massive stars, and because they're emitting powerful winds, when they are revolving around each other about a common center of mass, their winds will collide. And when the winds collide, that gives rise to a shock front and leads to high energy emission from that region. And when we look at this. High energy emission from different phases from Earth, we are able to explore different dynamics of colliding wind binaries at different phases. So I show here a simulation in which this one is the massive WR star, the heavier star. This is for WR22, in which one of them is a massive star. So this is a heavier star, and this is an O star, a smaller star. So when you'll see that when I run the simulation, the O star revolves around the WR star, and it comes so close to the WR star that it disrupts its wind at some point. So this is possibly the periostrone, and there is wind disruption going on, and this continues. So that is that. So around periostrone, when we can look into the X-ray emission from this kind of sources, it will give us a lot of valuable information. One thing we should consider is what happens to the shock heated plasma once there is a colliding wind. So that can be quantified by something called the cooling parameter chi. Now chi is a ratio of the cooling time for plasma to the flow time for plasma. And this is equal to the pre-shock velocity of the wind before collision, separation between the star shock and mass loss rate. So when chi is greater than 1, then the cooling time is much larger, so the wind expansion is mainly through adiabatic processes. The other is when chi is less than 1, that means the gas cools rapidly. So in this case, because so radiative shock basically happens when there is wind which is coming from one of the stars, let's say the WR star, and it goes to the O star, and the radiation pressure from the O star will stop the wind. So this V factor here decreases, and because of that, this chi becomes smaller. So when it is less, gas cools less rapidly, and we term that as radiative cooling. And related to cooling is something called radiative braking. So this happens in cases where there are unequal masses, like the example I was talking about. When you have a WR star, and which is coming at the winds of which are coming at a very high speed to the O star, then in that case it just breaks the O star just breaks the wind, and that leads to a sharp drop in the X-ray luminosity. So X-ray luminosity is a huge factor in determining which of these regimes are we talking about. For example, in case of adiabatic expansion, the X-ray luminosity falls smoothly as 1 by d, whereas in case of radiative braking, the X-ray luminosity variation is not so smooth. Next thing we should consider is how are these colliding wind binaries detected, and you may have already have guessed that it is detected by their variation in X-ray luminosity. For example, colliding wind binaries show greater luminosity when compared to single stars, and that is because when the winds collide, that is an extra source of X-rays. We have a strong increase followed by a decrease in the X-ray flux for a short time, and this is accompanied by an increase in the column density because of a lot of intervening matter coming between the observer and the colliding wind region. And also we are talking about shocks so there will be very many hot lines. So colliding wind binary, so we see this for colliding wind binary WR25. For example, this is the NH variation that you can see. Just note that the flux for X-ray variation. So this the authors here, detailed paper by Arora et al., where they have fit this entire spectrum with two different components. One is the soft component, which is for the individual stars together, and the other the hard component, which is for the hard X-ray winds from the colliding hard X-rays from the colliding winds. You see that when there is a generation of X-ray flux, when there's an increase in X-ray flux, there's also an increase accompanied by an increase in column density. And you see this for all of these other observations as well. So we know that colliding colliding wind, WR25 is a colliding wind binary, and as a part of the G2 observation, WR25 was pointed at with Chandra around periastron at two different phases, very close by. So these black dots represent the OB star, and this is where Chandra had seen it. Along with this observation, there are a couple of other observations as well. Which are a little off axis and where we don't have the spectrum, but we can where we can't use the spectrum, but we can use the fluxes of this to understand the X-ray luminosity. So something about WR25, it has a period of 208 days, eccentricity of zero point 0.5, O mass is 27, and WR mass is 75. So it's a heavy star, and one thing to really note about this kind of heavy stars is that they are at the end stages of stellar evolution, and therefore they will likely undergo supernovae and end up being a black hole. So it's very interesting to understand them as well for other astronomical reasons. Um, so this is the HETG spectrum before periastron. You can see this gorgeous spectrum, and it has a lot of emission lines. And this is the very hot emission line that I was talking about that arises in the X-ray collision, the wind collision region. It has a combination of a lot of other lines. We have for example, the hydrogen-like, the helium-like lines for silicon, the helium-like lines for magnesium, and so on. So when we have these helium-like lines, they are brilliant to understand the diagnostics. So a little bit of background. We know that the helium triplets arise because of mm, transitions going in three different levels. For example, when it goes from 1p1 to ground level, that gives rise to R emission. This is the I emission, and this is the F emission. Now this state here is metastable, and when so what happens is when there is a large UV field. For example, if there is an UV field coming from an O star, then this state is depopulated. So when this state is depopulated, the F lines decrease, and because there is an decrease in F lines, the ratio R equals to F by I is very sensitive to the presence of UV radiation and also electron density. So if the F line is eliminated, then we can say that there is a UV radiation possibly from an O star nearby. So let us see what happens for WR25. So this is for silicon 13, and this is the R line, the I line, and the F line, and you can clearly see that the F line is determined. It can be constrained very well, and we can clearly see it in the spectrum. Now, less energy is required to depopulate magnesium, but even in this case, you see that this red line here is the forbidden line that you would expect in case of no excitation, and the blue is what we see. So you see that even in this case we can see the F line as well. So the F line in WR25 is not destroyed, which tells us that the wind emission, the X-ray emission is not close to the O star, but rather at some distance from the O star, possibly in the colliding wind region. So this further affirms our understanding that WR25 is a colliding wind binary. Now, so this is what we get. So upper flux is consistent with no photo excitation. So therefore, X-ray flux comes from a shock cone far from WR and the OB star. Now, also notice that there are a lot of, these lines are really broadened. So emphasize that I'm showing here, this is the data that we have obtained for silicon line, and this is the same lines for similar ratios, but for the resolution of HETGS. And you can see the instrument is the lines are much broadened over and above the instrument resolution as well. So this is true for most of the other lines. You see this is the width for all the other lines, and so what we had done is this black lines here denote the Gaussian fits, that is the parametric fits for each of these lines, and this gray lines here denote the plasma the piecewise plasma fits. So you see that it doesn't really show a correlation in the full width, the width to the wavelength, and that is kind of expected because this is not a spherical wind flow, whereas in case of spherical wind flow, because the opacity increases with wavelength, what you see is these lines, you can see much deeper into these smaller wavelength lines, and these are the ones that you'll see only at terminal velocity. So this is you see an increase in the width versus wavelength for spherically symmetric winds, but that is not the case here. So that further affirms our understanding that WR25 is a colliding wind binary. And depending on the phase that we are seeing it, for example, this is the shift in the velocity, and this is the current observation that we are seeing. So we see a part of the plasma is really coming towards us, and the part of the plasma is going away from us. So because we see a net blue shift, it indicates that the blue segment which is going away from us is what we are seeing here. Um, so this is what we can obtain the and we also looked into off-axis observations like I've shown earlier. It doesn't really show a 1 by d variation, which shows that possibly there are more radiative processes that are prominent in WR25. That is also seen in the swift excited light curves. For example, these are the soft X-rays in red here, and these are the hard X-rays in blue here. It doesn't really show a 1 by d variance here. And also note that you see this because there is an extinction of soft X-rays. This possible dip arises due to absorption and not because of disruption of the wind in some systems. In some systems, like what you see is you see a disruption of winds because of the radiation from the O star. That is not what is happening here in this case. So, really, what next are we thinking about? In order to understand the system better and to understand the physics of this better, we would need observation at two different phases. This is the current observation which we have analyzed. Now, if we have two different observations at this phase and this phase, for example, in this case, we would expect less absorption and maybe less broadened lines, whereas in this case, we would expect more absorption. So, we could look into different regimes and understand their high resolution spectrum and understand more about the physics of this kind of objects. Yeah, so we one advantage about W25 is that the orbital period is nearly 208 days, so we can perform both these observation at different phases in a year, unlike many other colliding wind binaries that has very long periods of the order of years. Although the source is at high ecliptic latitude and it's a challenge for Chandra to observe it, but really the returns are very high. Thank you.